Okay, so for tonight, I am very pleased to introduce our speaker, Devin Conathan. Devin is currently a senior data scientist on the machine learning research team at American Family Insurance. In his current role, he enjoys developing full stack solutions that leverage state of the art machine learning research. His recent work mainly involves natural language processing, information retrieval, knowledge graphs, and knowledge graph embeddings. Feel free to ask questions in the chat box throughout. I'll read them to Devin at the end of the presentation in roughly the order that they were asked. I'll pass it to you now, Devin.
Oh, great. Great. Thank you for the introduction, and thanks for all the people for attending this this talk virtually. So yeah, so I'm going to be talking about tools and techniques for bringing machine learning research to production. And so, you know, that's probably could have come up with a more succinct title for that, but yeah, that's the general idea. Yeah, so Rebecca and I were talking. You know, I'm on this machine learning research team, and so the way it generally works is we kind of split our time 50-50 from in this research world, and which is more kind of like academic in nature, and we try to publish papers, and then more kind of like maybe traditional data science and machine learning work, where we try to develop solutions develop solutions and develop products for our business. And you know, in the best case scenario, we get to take the ideas that we research and bring them over to these solutions. And it turns out that that's a really hard kind of thing. It's a really hard problem to solve of how do you bring research to production. So I deal with this problem a lot, and I like to think I have some nice tools and techniques for it, and I like giving this sort of talk. So yeah, that's what I'm going to talk about today. So just a high-level overview of what we're talking about. Oh, I meant to get rid of that here, but so why this talk? You know, I talked a little bit about this. You know, this is just a really hard problem, and then I'm going to talk about kind of like big picture lessons from software engineering, you know, like ideas that we can borrow from software engineering to help make this problem easier. Specifically, I like to talk about, we spend some time talking about the Python packaging system, which I think is a very powerful tool that all data scientists, machine learning engineers should become very familiar with. I hear like a lot of people mention in passing, oh, you should learn how to package your code, but they don't necessarily actually talk about what that means and the tools that are available. So I like to spend a little bit of time on that. And then I'm actually just going to have like a demo research project and walk through and kind of give you an overview. So I've given a couple of versions of this talk before, and some of those, usually I just kind of like pitch all these ideas, but for this project, I wanted to do something a little different, or this talk, I wanted to do something a little different and actually just kind of put my money where my mouth is and do a fun side research project and apply these techniques to that. And I think it worked out pretty well. So hopefully you get something out of that. So a little bit about me. So Rebecca gave a little bit of an introduction about my work, but just more about a little bit about my background. So currently I live and work in Madison, Wisconsin, which is where American Family is headquartered in. I grew up in Hudson Valley, New York. I went to school in Ithaca, New York. I did live in Chicago for a few years, and my wife went to University of Champaign-Urbana. So I lived in Urbana for a few years. Undergrad, I studied math and philosophy, and I studied machine learning as a grad student. And these last 2 points, you know, so I worked various odd jobs between undergrad and grad. And I also like to mention that, you know, I didn't learn to code until grad school. So, you know, I did study math as an undergrad, but you don't learn coding as a math major. You learn really theoretical abstract stuff. So anyway, I like to just mention these last 2 points whenever I get a chance at talks like these, because you know, if you're sort of outside this field, it can be a little intimidating to break into it. And you know, as someone who was working various customer service and food industry jobs, I thought I would never be able to get like a technical job like this. And I sort of just, bit the bullet, went to grad school and kind of taught myself how to code, and here I am. And so, I wish I had someone like me telling me, hey, just do it. So if you're not sure and you're intimidated, like everyone's intimidated, just do it, go for it, and don't be scared. Yeah, so moving on to like, why is this kind of like research to production kind of pipeline so hard? And I think one of the key things is that, like research and software engineering kind of like fundamentally are very almost like opposite things. So like research on one hand is that it's very personal. It means something different to everyone. It's ephemeral. A project you're working on today might disappear in a few days, or you're probably going to move on to something else. It's dynamic, so it's changing. It's vague. By vague, I mean like success is hard to define. It's not even clear like what is successful and unsuccessful research. Whereas software engineering is like mostly the opposite of all these things. It's the opposite of personal. It's designed to be, to work. It's be agnostic as to the person who's running it. It's designed to stick around for years, if not decades. It's designed to always be the same, and success is very easy to define. Like, does your code run and does it do what it's supposed to do? And so there's a tension between these two kind of like fields. And so like blindly taking like software engineering techniques and just saying like, apply them to research doesn't work. We're dealing with a lot of that, like trying to take like Scrum and Agile techniques and applying them to research, and the ideas don't necessarily translate. But still, I think, at a high level, there are lessons that you can borrow from software engineering to make research more streamlined, and especially to bring your research projects to production and turn them into software. And so, just at a very high level, I'm going to do a deep dive into some of this stuff. These are the things like I like to highlight. Data structures are key. So there's a reason in computer science 101, you just start with data structures because they're kind of essential. I mean, usually in the software engineering and computer science world, data structures is taught from the perspective of like the algorithm and the computer and how to make the algorithm as fast as possible or as scalable as possible. And usually in the kind of like in the data science world, it's kind of more data structures are there to make your code easier to read by humans. So I think that maybe they're obviously you're also thinking about data structures from a performance point of view, but having the right data structures is kind of key to making your code readable, both readable and extensible, if you want to kind of like bring more research ideas into your software. Consistency and reproducibility is obviously very important in software engineering. You want your code to kind of run day in and day out and do the same thing over and over again. This is also a big kind of like problem in research, especially machine learning, where there's a lot of randomness. There are basically ideas from software engineering that we can borrow to kind of make your code, make your experiments more consistent and more reproducible. This next point, I'm going to spend a lot of time talking about, but packaging your code. So the idea of, thinking about your kind of research project as something you can package and ship off to something and have it be able to run on someone else's computer. These are things that are important to think of, and there's a lot of, basically this is kind of like the foundation of software engineering, is like building these packages that can then be shipped to other computers. So there's a lot of tools and techniques that we can take from that. I feel like every talk kind of like this talks about tests. And this is another area where there's one of these tensions, because testing to a data scientist means something very different than testing to a software engineer. So like data scientist tests usually mean what's your accuracy on your test set, whereas software engineer is like do all your unit tests, which test the individual functionality of all your functions. Do those all do the right thing? So I think there's a middle ground between these two. And I'm going to get to it a little bit later when I kind of do the review of my project. And I think I have like a pretty sensible, at least like place to start, where you have some tests, but you don't go crazy and test every little thing, because that's one of the problems of kind of unit test research, is the research is always changing, and you don't want to have to spend all your time writing your tests only to have to rewrite them the next day. And then lastly, there's like this field of continuous integration, continuous deployment, which I think is like especially a nice fit for research, because the idea is, research is always changing and dynamic, and continuous integration, continuous deployment lets us, incorporate those ideas from research into our product as quickly as possible. And the tooling around this is getting like better and better and cheaper every day. In fact, if you have a GitHub account, you can start playing around with CI/CD today for free. And I did that for this project. So I'll show you how to do that. It's pretty cool. If you haven't dipped your toes in this waters, it's a good time to do that. So yeah, so I wanted to talk about like Python packaging 101, because I think this is, this is really essential. And so, just to mention here, like I think throughout this, like I kind of try to include a little bit for everyone. So there's some like, I start out like really basic, but I get pretty complex, and there's a lot of moving parts going forward. So I hope there's a little bit of everything for everyone. Yeah, so I wanted to start out just really basic packaging 101, and I wanted to establish some terminology, because I hear these words and phrases kind of used interchangeably a lot. It's important to make sure we're all on the same page. So if you have main.py, that is what I call a script. And that's just a Python file that has a bunch of code, and you're supposed to run it, and it does something. Maybe it prints something in a terminal or creates a file or whatever. But it's not meant to be like a part of a larger system. Maybe it uses a larger system, but it's just kind of like a standalone thing. Contrast that to like maybe utils.py, which is a module. So you're not supposed to like run utils.py. It just contains a bunch of functions. That's maybe main.py uses some of the functions that are in utils. And so you can import stuff from utils. And the name module comes from the fact that it's sort of like, it's modular. You can kind of like slot it into different places. And then what a package is in the Python sense is simply a folder that contains a bunch of modules. And so here I've got a package called stuff, and there is a special module called dunder-init.py, and that just tells Python, hey, this folder is actually a package, and you can import it. And so it lets you kind of like organize like a collection of modules that may be kind of a part of one particular system into one package. And then a library is kind of the next step up. It's just a collection of packages, e.g. the standard Python standard library. And packages can contain like other packages or sub packages. So at what point does a package become a library? I don't know, but so I think it's fairly okay to use package and library interchangeably, as long as it's a big enough package, I guess. But yeah, so just wanted to talk about some terminology before we go into it. So now I just wanted to do some kind of like fun with the terminal, where I talk about Python's packaging system. So I've got an empty directory here with a fresh virtual environment, a Scratch environment. And so I'm going to make a package. I'm just going to call it some package, and I'm going to create that dunder-init file. And this lets me like, let's add something to that dunder-init and say hello equals world. And now, so I can open up Python terminal, and I can import some package. Oops, this is where the live coding part is not a good idea. And I can call some package.hello and get world. And this, I'm able to import it because it's sort of like in my current directory, so it's in my path. But maybe you want to like turn this into a package that you can ship off. And the way Python does that is you create a script called setup.py. And in setup.py, you import a function from this package in the standard library called setup tools. You call this, import this setup function. And then I'm also going to import this useful function called find packages. And so you call the setup function, and there's a few, lots of arguments you can pass to the setup function, but the essential ones you'll need are name, some package. And so this is like the name of your package. So if you were to publish this to PyPy and then like make it so other people could pip install your package, they would pip install what the name is here. So pip install some package. So this would have to be unique. Version, you probably want to include a version because versioning your package is important. And then finally, you just want to say, list the packages you want to include in this package or library you're distributing. And that's where this find packages function comes in handy. So this would just be a list that contains, say, that folder, some package. This find packages function just like finds that automatically for me. And so now if I run setup.py, I mean, I could just run it and it will say no command slide. If you run Python setup.py install, it actually just installed my package into my virtual environment. So you can see it created a bunch of folders, a build and a dist. But so I can like, let's say I go into here, and there's some stuff in here, but I just want to go in here to demonstrate that I can import some package, and you can look at it, and you can see it's no longer the thing that's in that Scratch folder I was looking at. It's actually in my virtual environment, and I can call that and take a look at that. So that's kind of like the bare bones basics of what you can do. So let's uninstall, uninstall. There we go. Oh, forgot another end. Okay, so that's the simplest way to install something. So let's say I don't want to install it. I just want to like kind of create a package that I want to give to other people. So I'm just going to delete these dist and build folders because I want to talk about what they actually are. So if you run setup.py, there's a couple different ways to like, create packages. The simplest is called an sdist or a source distribution. And what this does, if I go, it created that dist folder, and if I go in there, it created this archive, and I can untar that. Well, one, I can pip install this, so that's cool. And then, but I kind of wanted to just let's see. And you can see all that did was take the setup.py and my package and put it into this archive along with a bunch of other metadata. So that's all the source dist is a, you're just distributing the source of your package. Another kind of like a better way of distributing your package is a build distribution. And there's a couple different ways of sort of packaging a build distribution. The standard way of doing that today is a wheel, and that's sort of the recommended way. And so what this does in this dist folder creates this .wheel file. And again, this is something I can pip install directly. It's going to complain that I already have the package installed. Well, what this is just a zip file. And if I look in that, So this is all that's in the zip file. And so most importantly, you'll notice the setup.py is not in this file. It just contains, it contains some metadata, and it contains the setup, just the package and the package code. In this case, just this one file. So that's a key distinction between the build distribution and the source distribution. Obviously, this doesn't really matter for such a small package like this. But if you take like a large package like TensorFlow or PyTorch, and you try to do the source distribution of it and install that on your machine, so one, it's going to be a pain in the butt because you have to have all these requirements to even install, run the setup.py and compile all the files, because there's a bunch of C code in those packages. And it's going to take maybe an hour on your machine because you need to compile all this code. Whereas a build distribution, you compile it ahead of time, and then you take the output of what gets compiled and distribute that. And so when I run the pip install of this wheel file, literally all it does is unzip the file and copy the files into the virtual environment, versus the source distribution. When you install it, it actually kind of runs that setup.py. So that's a pretty key distinction, important to understand the difference there. But the takeaway is, if you want to do some weird stuff with the setup.py file, you might want to do the source distribution. But the most kind of portable and easy way and kind of most efficient way to distribute packages is with the wheel, because installing them is literally just copying some files. That's why you can pip install Torch, PyTorch, or TensorFlow on your machine, and it just takes a few seconds. Yeah, so that's what I wanted to talk about mostly with that. There's a bunch of other stuff you can do with the setup.py file. And I think I'll just wait until I go through my demo project to go through that. So I'm going to go back to my slides now. So now I wanted to move on just to, the part, like I said, where I put my money where my mouth is, and just I did a demo research project, and I just want to kind of walk through that. So basically, Rebecca mentioned in the intro, my kind of research at work is kind of primarily in the fields of natural language processing and information retrieval. So I wanted to take the stuff that I do for work and apply them to something fun, and that's what I did here. So this is going to be a bunch of crash courses about what all these things mean. So again, this is just to give you the bare minimum so that you understand a little bit about what's going on. And so hopefully, some of you are somewhat familiar, and hopefully there's something new for everyone. So information retrieval is pretty straightforward. It is literally retrieving information. And our kind of quintessential, this is a very meta explanation of what information retrieval is, but the quintessential information retrieval solution is Google. And so the idea is, in information retrieval, you have a query and you've got a corpus. In this case, in Google's case, your corpus is all of the internet, and you want to find the appropriate document, web page, resource, or whatever that's in your corpus that best kind of answers the query. In this case, the Wikipedia page on information retrieval is the best answer to this question. And as you can see, there's a pretty good answer to information retrieval, which is maybe slightly more technical than the one I gave, or maybe not. So that's what I want to talk about there. Next, I want to talk about transformers, which is a recent kind of, it's basically the state-of-the-art natural language processing model today, introduced just a few years ago, but it's quickly becoming the standard for doing anything interesting in this field. I could spend a whole hour talking about transformers, but I'm not. But what you need to know for the purposes of this project is that transformers are a machine learning model that takes as an input a string or a text, and outputs a vector. And so in this case, I have the text, what is a transformer, and it outputs the vector 2, 4. In reality, the dimension is much larger than 2, hundreds of dimensions, but obviously that's pretty hard to visualize. And so lastly, I want to give you a Magic the Gathering crash course. And so this is one of my hobbies. If there are people who are into Magic here, I'd love to talk about it, maybe offline. So, but the idea is, so Magic the Gathering is a trading card game, and you have cards that look like this. And the object of the game is to, you have like 1 versus 1, and you're trying to do damage to the opponent, and all these cards represent spells that interact with the game or interact with the players in various ways. And the important point here is that each card has a name, in this case lightning bolt, and each card has some rules text that says what the card does. In this case, lightning bolt deals 3 damage to target creature or player. So putting it all together, what am I proposing as a research project here? Given a query, use transformers to find all similar cards to that query. If you put in the query lightning bolt, you might get, you would find the card lightning bolt, but you might also find the card feedback bolt, lightning strike, precision bolt. You can imagine the naive thing to do would just be like find all the cards that have the word lightning and have the word bolt in them and return those. But if we use transformers and their ability to kind of interpret things as vectors, we can think about like what are the semantics of the word lightning bolt and what are the semantics of the rules text, do 3 damage to target creature or player, and maybe we can find cards that do similar stuff to these cards, but don't share the same exact words. So this is like a common trend to try to take these like more natural language understanding type models and apply them to this field. What does it all look like as kind of more concrete experiment? Another reason I wanted to chose Magic the Gathering as a sort of like data set, if you will, is it's really easy to get to download a JSON file of all the Magic Gathering cards in existence. So that was really easy to get. And so you can process that and get these name text pairs. And the idea in the information retrieval sense, we're going to try to, we can treat the name as like our query and the text, the rules text of the card as our true context, like the best context that matches that query. And so that way we get, each card becomes a training example for our model. So we get basically like a bunch of, there's tens of thousands of cards in existence. So we get a bunch of like free training data for this problem. So it was like a fun problem to work on. High level overview of the model. So we have 2 transformers here. One is going to turn the name into a vector, the name of a card into a vector. One is going to turn the rules text of a card into a vector. And then we look at the dot product similarity of those vectors. And if it's a high similarity, we say, yes, this card is a good match for this name, return it, and otherwise don't. And then in terms of kind of like a research, question with these transformers, there's a lot of different architectures and hyperparameters. And so we want to say, try out a bunch of different of these. You take the data and each kind of version of this model is an experiment. We run a bunch of experiments and we take the best experiment and can we deploy that as a web app that anyone can use and search for cards. So now we're going to just move on to this project and kind of walk through it. So I pretty much just spent a weekend working on this project. And I'm just gonna, and this is on GitHub, so I'll share the link, I guess, when after the talk, so you can explore it on your own. Let's, I'll kind of like walk through it. me do a quick time check. So we've got about 20 minutes or so. So I think I can give a whirlwind tour. There's a lot going on here. Again, I hope there's a little bit of interesting stuff for everyone. But yeah, let's talk about the setup.py since we were just talking about that. So this is maybe like what a more interesting setup.py looks like, maybe what you're more used to. So the name, we still have a name, we still have a version. Here I'm importing the version from inside the package. And then we have the packages. So install requires, this is, you're probably familiar with what this does is, in order to run this package, you need a bunch of other libraries like PyTorch and transformers and et cetera. And so this, when you install this package, it installs all these. Extras require is another thing. Maybe you've seen, so basically what this means, if I do pip install mtg search and then do train in brackets, it will install these packages as well as these packages. And so basically this is just saying, in order to train the model, you need to install these extra packages. So install that version. Console scripts is entry points console scripts is a interesting, basically this lets you define a bunch of commands that will get added to your path when you install the package. And basically says the mtg search command will run the main function of some module inside my library. So, so if I open up a terminal, I've got this package installed in this environment. If I run mtg search, it actually runs a file that's in here. And so that's a nice way to build a command line interface to your package. And then this is kind of maybe the most unconventional aspect of this, but I think it's really important, especially for machine learning research projects like this. So package data, so find packages or packages is what kind of like looks through all the Python code and automatically includes all the Python code as part of your package distribution. But what package data does is it lets you define non-Python files to also include with the package. So in this case, most importantly, we're going to include the model itself when we distribute our package. And so that's a kind of an important distinction as opposed to like saying like, oh, in order to get my model, you need to, or in order to run my model, you need to clone my repo and follow these steps to get the model and whatever. No, it's like, no, we're distributing a like fully encapsulated working version of this, as a product and saying, when you pip install this thing, you can run all the functions that I include with it, including the ones that need the model. So that's an important thing, aspect of it. And I'll also point out that I included this at the beginning of the setup.py. And basically, this just, we talked a little bit about like unit tests, and I would consider this maybe like a basic unit test of like this. Basically, what this says is don't build the package unless the model exists. And you could build a development version of the package without the model. Yeah, so basically, like you're at this point, like you're guaranteed if you're distributing the package that it's going to include the model. So yeah, so that's all I wanted to talk about the setup.py. So I'm going to kind of just give a quick overview of some of the important modules and packages inside my package. So almost all of my machine learning research projects look somewhat like this. So I always include a constants.py, which defines, all my paths to my data files and directories and stuff that, not going to change really. If there's like a database involved, I'll include like, where the database is in this. Yeah, so highly recommend a constants.py file to define that sort of stuff. Let's talk about data. So that's always where I start. And I usually define, my data looks like this. If I have like various data sets, I'll also have like a data sets folder. But I always define a data classes folder, or module. And this is where I define all the data structures that, kind of my model interacts with at various level of pre-processing. So like, our kind of more raw data is just like, what is a card? And then all the way down to like, what is a training batch? And so you'll notice that all these are these data classes, which is a built-in a utility class in the Python standard library. I highly recommend that you use them because this kind of gets at that, makes your code, the data classes are not for computers, they're for people. So, it's really easy to look at this class and like, okay, what is this class? Oh, it is a class that stores data and the schema looks like this, and it's got two properties, name and text, that are strings. So it's like, just by looking at it, I don't even need any, documentation or docstring or anything. Like, you can just look at this and say, okay, I know what this thing is. And similar for the rest of the things. And then I'll talk about data modules. So I use PyTorch. The name of this comes from PyTorch Lightning, which defines this concept of a Lightning data module. So PyTorch Lightning is a super helpful package or library for training PyTorch models. Highly recommend it if you use Torch to train your models. And basically, this just defines kind of like the logic. It encapsulates all the logic about taking your raw data and splitting it into train, test, and val splits, and pre-processing the data and getting your data loaders. Kind of like wraps it all in one nice little helper class. So that's all I wanted to talk about data. So next is models. In a typical project, I might have like many different folders with different kinds of models here. For this project, I just had time to try out one model, this transformer model. But similar here, I love data classes. And what is a model? What is a machine learning model other than basically a function that takes an input and returns an output? And so really easy to define those here. And then PyTorch Lightning also has defines this Lightning module, which is essentially a Torch, a PyTorch model, but it takes care of a lot of the kind of boilerplate code. So you don't, you get to write the stuff that you're interested in and don't have to deal with all the sort of training logic and all that. So I'm going to gloss over all the most of the details there, but basically that's just a class that defines the model and defines all your kind of training sets. And important things I like to highlight here that you get basically for free with PyTorch Lightning. So I define this main Python file, and basically, this gets executed. So this transformer.py is also a script. And with PyTorch or PyTorch Lightning, they have a way of automatically inserting a bunch of basically the keyword arguments that you could pass to a trainer as an argument parser, and so you can just pass them as flags to your command line app. So that's cool. You get a bunch of stuff for free there. Then this model checkpoint callback will automatically save the model for me. So that's cool. I don't have to worry about that. And then for this project, I'm using Comet. It's called Comet.ml or Comet-ML. It is a model sort of experiment tracking software. And there's a bunch of kind of variations of this, weights and biases, ML flow, Neptune AI. pick one of those and use it. It's super helpful for projects like this. And basically, this every time I train a model, it logs all the data, all the hyperparameters and all the kind of results to this like web app, and it stores that information for you. And kind of most importantly, well, so it gives you kind of like an overview of like how long it took to train each model, and you can kind of quickly see, oh, I trained a few versions of this model, but this is the only one that did any good. It got 70% test accuracy, so that's what I want. And most importantly, you can kind of view the training curves, and you can see, okay, it seems like the model converged. And then most importantly, it gives you this experiment key. This is like a unique identifier for this version of training the model. And the way I set this up is the model checkpoint automatically saves the model in the models directory with that key as the folder. So if I go into this models directory here, I have two versions of the model that I trained, and basically so this way I can kind of go through all the experiments, find the one where that I want to keep, and then the way I've set it up is that in this checkpoint.py file, I define the checkpoint, and I just have to put that model key inside this checkpoint, and then this checkpoint variable is what defines what version of the model gets packaged when I build the package. So putting it all together, basically, you just have to look at your experiments, find the experiment of the best performing model, and then put its experiment key here. And then when you build your package, that's the model version of the model that gets built with your package. So super nice workflow there for managing lots of different experiments. And then finally, I wanted to talk about the API. So like everything we've talked about so far is more on like the model development side of things. But at some point you want to like deploy or share your model. And that's where the API comes in. And so the API is like the application programming interface, but it's like basically like makes you think about like, okay, how does the outside world going to interact with my model? And so I usually define an API folder, and in particular, I'll define, maybe I'll define a web app, which will serve an endpoint of how to run the model, a command line, which will let me interact with the model in the command line. But kind of common to both of those is this main API. And kind of defining this file just like really makes you think about like, okay, what are the essential things that the outside world is going to want to do with my model? Kind of fundamentally, we're going to want to search. In order to search, what do you need to do? You need to be able to create an index. You need to be able to load the query encoder. The query encoder is the card name encoder in this case, and the context encoder or the rules text encoder in this case. So you need to be able to like, load your models, and you need to be able to search for them. And that brings me to the tests. So obviously, like there are like a lot of stuff going on and all these things, and you can write tests for every little part of it. And maybe if you have a lot of like data pre-processing logic, you probably want to unit test that in some sense, because it would suck to get very far along in this process and then find out you have a bug in your data pre-processing. But at a bare minimum, you want to test your API. And what I mean here is basically kind of like everything in this main.py gets a test in my test API folder. So can you load the query encoder? Is it an instance of the right thing? Can I load the context encoder? Same. Can I load the index? And finally, can I run a search? Does the search return the right thing? Is everything in the list that the search returns of the right type? So it's pretty kind of like high level tests. But as you can see, like, and there's a great function or package called PyTest, which will automatically run. Basically it just looks for words, modules with the word test in them and just runs them. And so basically, I can run that, and as long as that test passed, it's sort of like I'm guaranteed that my app is going to work, because basically the core functionality of how I want the outside world to interact with my model works. So that's cool. And again, so going back to testing can be very cumbersome if you unit test every little thing. Here, I've just written 30 lines of code, and it guarantees that my model is going to work. So that's great. It's not a big ask to write tests like this. So that's the kind of whirlwind tour of the package itself. And finally, I wanted to talk about, okay, now I want to deploy this model. What does that look like? So here in the infra directory, this is where I keep all the sort of configuration files to configure infrastructure. I don't think I have time to kind of dive into this, but basically these are all Terraform files that define, that basically in a declarative way define a bunch of AWS infrastructure. And I could go in from the command line and run some Terraform commands, and that this will automatically kind of create all this AWS infrastructure that will run this code for me and serve that web app that I showed you. But I don't want to do that. I don't want to have to do that sort of manually. We want to automate that as possible. And that's where the CI/CD part comes in. And so in order to do that, in GitHub has this new feature called GitHub Actions. And what you do is you create a .github folder, and at the top of your repo, and create a workflows folder in that. And you create, you can put a bunch of YAML files inside that workflows folder. And what this is just essentially a configuration file that configures a bunch of scripts that run when I push to the repo. And so I will just push a new version of this just to demonstrate what I mean there. So let's update the version, update a new version of our package. And let's see, bump version, new deploy. In the real world, I might create a pull request, but obviously I'm not changing any features here or anything like that. So if you go to the repo and so here's the repo for this, and if you go to this Actions tab, you can see basically this is GitHub Actions, basically kind of looking at that file and running all the commands that are in that file. So this takes about 5 minutes. So while that's going on in the background, I'll go back and kind of walk through the file and what it does. There's a bunch of kind of like pre-canned actions here, but essentially it runs on a Ubuntu server. It installs Python, installs all the dependencies. It configures AWS credentials. So there's a way of kind of storing secrets inside of GitHub. Because we'll need that because we want to deploy our stuff to AWS. We download the model. I didn't have time to get into it, but DVC is data version control. This is another great kind of utility to use for kind of versioning your models. And this is basically an easy way to download the files from download the model files from S3. I run the tests. So if any of these commands fail, the whole thing stops. So, run the test because we don't want to deploy a non-working version of our package. We build the package. We log into ECR and build a Docker image and push that. And then we run the Terraform commands, which stands up all the infrastructure. And then finally, we test the endpoint. So that's basically kind of like a whirlwind tour of GitHub Actions. And so this is something if you have a GitHub account, you can do this for free. Obviously, you have to pay for the AWS stuff. But if you want to just have like something that runs, installs Python, runs tests, and like builds your Python package, you can do that with the free GitHub account. You can get I think like 2,000 minutes per month or something of a server running, and it'll most actions will just take a couple minutes. So pretty much as long as you don't have like a ton of crazy projects, we'll let you do whatever you want to do. Another thing, one last kind of like best practice from the sort of CI/CD world I'd like to point out here. So I actually have two branches. I have this main branch and I've got a prod branch. And so to refresh that, but there's a kind of a practice that where you have a branch that corresponds to a sort of a prod environment, and basically whenever I push a change to the main branch, it automatically deploys, and I call that my sandbox environment. And so that way I can do like development and test new ideas and maybe break stuff. But it doesn't affect anything that's on the prod deployment. So even though right now I'm in the middle of deploying a new sandbox version of this because I pushed this to main branch, I still have a working version of my prod app that I can go ahead and show you. So I can do my search for lightning bolt and get lightning bolt is the top hit, but I do get feedback bolt, lightning strike, precision bolt, all these like kind of similar things. Fun takeaway from this project, it kind of works. So there's shock is another kind of similar card, and you get similar stuff. So like I didn't know, heat ray, this doesn't have the word shock in it, but it does do similar things to shock, so it makes sense that it might show up. And then you can just obviously like I don't know, come up with like ridiculous things and see what comes out. So Mr. Sandwich, the top matching card is the cheese stands alone. Makes sense why that might show up. Like, I don't know, do that. And then you get all these like kind of like funny sounding card names, which kind of like seem like they might match with Big Beefy Boy. So you can have all kinds of fun with this. And I think this is something I want to kind of maybe keep developing because I think I'm onto something. I showed this to my boss, who's also into magic, and he thinks there's something valuable here because a lot of the applications out there for searching magic cards don't do smart stuff like this, and they're hard to use. So with that, you can see this is still building. Looks like it's about to deploy. I think I'll wrap things up there and open it up to questions. So I haven't been paying attention to the chat or anything, thanks for bearing with me through all that. So I will happy to take questions.
Thank you so much, Devin. I love this talk. We don't see a lot of live demos here.
Okay,
so
cool.
I really appreciate it. Yeah,
cool.
We have a handful of great questions. The first one is from Kevin Oliver, who's excited about magic.
Okay,
and
awesome.
He asks, how would you capture the mana cost if you wanted to do that as well? Yeah. Would a CNN be the way or a different kind of transformer?
Yeah. Yeah, that's actually, I wanted to, if I had more time, I would have come up with like done the next iteration of the model. So yeah, so basically, you know, kind of like the baseline thing I would do. So that kind of gets at, you know, we're changing our fundamental data structure. So like, you know, right now a card is it's just a name and a text, but I would, you know, could add some fields here, you know, color, string, and then, you know, mana cost, etc. Maybe that's I guess that wouldn't be an int, but anyway, you'd come up with add a bunch of new features. You know, there's also like card type, etc. Yeah, and then I'd probably come up. So in that case, we'd probably need a new data module. Or no, maybe we wouldn't. Oh yeah, because we would need a new sample, which had maybe a structured field for the query, and then but then the idea is you come up with a new model, and I think like as a baseline, I would just concatenate all that stuff as one input. So just like you know, the rules text followed by the type and the mana cost and the color, and just like make it one blob of text, and seeing kind of comparing the test and train, or sort of the train and val results with that. But yeah, to get maybe at the root of your question, I'm really interested in kind of like I mentioned, you know, some of my background is in knowledge graphs and knowledge graph embeddings, and I think there's some ways to borrow some techniques from that. I think transformers really have a way of capturing some, kind of like graph structures, and so I would try to find some way of, you know, how can I come up with embeddings of a color, type, a mana cost, or whatever, and combine those. You know, come up with a new kind of transformer architecture that is able to combine those all into one vector. But anyway, I could probably talk about another hour about what I want to do with that. But that hopefully that's a good answer for now. I don't know how many questions there are, so
yeah, there are 4 more, but sometimes
okay.
questions keep coming. So
Okay.
we'll do a couple more.
Okay.
From Sagar Minocha, is it standard practice to include the model with the package, and what's the size of the model?
Yeah. Okay. Yeah. That's one thing I didn't mention. Part of the kind of like research challenge I wanted to give myself is making it a small enough model, both to like make it easy to package and to make it so I could like kind of quickly iterate on ideas and load it for the sake of the demo. So I am, as my like base transformer, using a tiny BERT, which is just a 2-layer BERT that Google released as one of their papers. And so these models themselves, I think they're just like 20 megabytes each. Let me see. So I don't know if I can see the file size in here, but yeah, I think they're like 20 megabytes each. So in this case, these models are pretty small. But yeah, typically these transformer models are quite large, you know, a couple hundred megabytes and millions of parameters. And I would say, you know, if you're planning on kind of hosting the package in, you know, in PyPy or in some sort of package distribution, like GitHub lets you actually kind of have your own private like package registry to just host and distribute your packages. And there is going to be a file size limit to that. So I would say in that case, it is not standard practice there. And so if I were under those constraints, I would just, you know, put in some logic to just store a reference to the model and have it like download the model when you try to run it. Another option is if we are doing the source distribution method, I haven't actually tested this to see if it works, but I don't see why it wouldn't work, is to have it as part of the setup.py download the model, and so then you get the model when you pip install the package, not when not when you deploy it, or not when you kind of build the package. So that's another option. But in this case, since we're not uploading the package to any sort of package registry, we aren't really under those constraints. Like if you just look at the GitHub, this workflow, there is, we just build the package and then we add it to the Docker file. So it never actually kind of like leaves the model never kind of like leaves this area other than, being on the Docker file itself. I like to say, there's not a lot of, there's no wrong answers. I guess there's a lot of right ways of doing these things, as long as they kind of like fit the constraints of what you're given. And, so one constraint is you can't have packages above 50 megabytes or whatever the constraint of the package hosting solution you have, in which case, I wouldn't include it in the package there. But there are no rules against it. As long as it works and your test pass, you can do whatever you want, right?
Great. Yeah, I think we'll conclude with Kevin Oliver has a couple of more questions.
Okay.
Is Comet ML doing the hyperparameter tuning as well?
Mm-hmm. So it's not doing the tuning. It just, so in the, let's see, in the model, in this, when you load the model, here it is, Comet logger log hyperparameters. And then I just log this model.config file. And so it just logs them. So it just kind of like gives you a snapshot. So if I go here to a particular experiment, and I think there's a tab here for hyperparameters that tells you, everything about the model. So it just logs them. So Comet doesn't do any of the tuning for that. So the tuning I was all kind of just doing manually. I was trying various, there was one version of the model where I was like tweaking actually the number of layers and stuff. On that note, as part of the package, let's see, as part of the, let's see, is this? Here it is. Part of that share out that I mentioned today, where this other team shared out their kind of methods and techniques, they showed me this project called Orion. And it does hyperparameter tuning for you, and it looks pretty solid. I haven't played around with it a lot, but the next project I take on where I need to do hyperparameter tuning, I plan on looking into this. So if you're looking for a hyperparameter tuning solution, I would point you in this direction.
Great. And last question, could you show the form the card data is in that you're training against?
Okay. So yeah, maybe I can just do a quick form of what the data processing pipeline looks like. So the raw data, let's see. So this is this takes in the raw data, which is just this JSON file of a bunch of dictionaries that contain strings essentially, and I turn it into a bunch of cards. And so cards look like this. They don't have a color, but they have a name and a string. And then let's see. And then I take. Let's see. I think I do. And then I take turn those into samples, and I have this method to turn cards into samples. So essentially, a sample is the same as a card. It's just that we've renamed name and text to query and string. But this kind of like makes it so like this is what I would do in the information retrieval sense is I've got a query in a context, so it sort of like puts it into that agnostic framework. and then, and so that sort of sample is, and then a trained sample is essentially, is a, so when you pass it into the model, you give it a query, you give it the positive answer, and then you get a list of negative answers. And so like basically what the model is trying to do is kind of just basically do a multi-class classification problem, and say like, find the correct one out of this list of negatives and the positive. And then a batch is just a batch of those. And then turning a, so yeah, hopefully, I'm not sure exactly which step the question was asking about, so I'm just going to go through all the steps. So hopefully one of these steps answers the question. But and then we have that train batch, and that goes, that is what gets passed into our model. And then I have this function that turns a train batch into a model. And so this is what the tokenizer tokenizes the data. And so that turns it into a batch encoding. And then essentially what this is a, there's a few things you need to pass to a transformer model, but most importantly, it just tokenizes the text and turns it into a series, a list of token IDs. Maybe I can, and token IDs is essentially like basically a list of integers. And then the model knows how to turn the integers into the vectors. So let's see. This is where we get into the dangerous live coding part of the talk. But
yeah, Devin,
yeah.
Kevin wrote back and said just meant the form of the JSON file.
Oh,
Curious what
okay.
properties
Sorry.
came in from that.
Yeah. So yeah. So then we're talking about the raw data. So the raw data is, I got it from, I just searched Magic the Gathering JSON, and there was a pretty easy way to find it. But there is this data, and basically each data has every Magic the Gathering card set in it, and for each card set contains a list of cards, and then each card is a JSON which has all the metadata associated with that card. Most importantly, it has name and text, which is what we're using here, but it has all the other stuff like rules, type, power, toughness, cost, color, et cetera. As all the metadata you could want in this JSON, raw JSON. So
great.
Yeah.
Well, with that, thank you again so much, Devin. This has been
Sure.
a delightful talk. Thank you everyone for attending. This concludes our February PyData Chicago virtual meetup. We'll be back around this time last Thursday in March for our next one.